This video is part of the book Statistical Modeling with R that I wrote and published in 2023 with Oxford University Press. In this video, I'm going to talk about GLMs, generalized linear models, whenever the response variable is a count, starting with exploratory data analysis to be followed by the frequentist model fitting and the Bayesian model fitting. The codes and data to run this analysis are in the website shown in the screen. So many observational or experimental studies have a response variable that is a count. The Poisson and the negative binomial distributions are the most commonly used distribution to model response variables of this type. So here is the formula for the Poisson distribution with a single parameter, its mean, mu of y. And these are different shapes of the Poisson distribution. With increasing means of 1, 2, 3, and 4, and 6. Sorry. So as we see that as the mean of the Poisson distribution increases, the shape of the distribution becomes more symmetrical. The Poisson distribution has a peculiarity in that its variance is identical to its means. This means that each parameter, the mean of the Poisson distribution, attempts to do two things at the same time, which are to express the general tendency of the data, its mean, and its variation around the mean, its variance. The negative binomial distribution has a more complex expression. In this more complex expression, we can see in the right-hand side something that should remind us of the formula of the binomial distribution to which this is related. We see in the first term the capital letter gamma, which is a mathematical function that is analogous to the factorial function for real numbers. The negative binomial distribution therefore has two parameters, its mean and phi, which is called a dispersion parameter that we will talk later on what it means. So here we see for means of 1, 2, 3, and 6 the different shapes of the negative binomial distributions. The count GLMs, all regardless of whether we model the response variable with a Poisson or a negative binomial distribution, they all use a log-link function. This means that we estimate the parameters relating the explanatory numerical and or categorical variables to its mean. We model this relationship. This relationship is linear only in the space or scale of the log-link function. After estimating the parameters, where the model is linear, that is in the space of the link function, we invert the link function to obtain predictions, the predicted values of the mean from different combinations of values of the explanatory variables and its parameters, the betas. So all the probability functions stemming from the exponential family, except the normal distribution, have a specific relationship between the mean and the variance. A corollary of this statement is that whenever we model the effect of the explanatory variables on the mean, we are also modeling their effects on the variances, on its variance. So overdispersion is a feature that occurs in count GLMs. In GLMs having a counts as a response variable, and it refers to the fact that there is an excess of variance in the data with respect to what is correctly modeled in the count GLM. The account GLM has overdispersion whenever there is a criterion that we are going to see later on how to calculate it. Whenever this criterion of the residual deviance divided by the residual degrees of freedom is greater than 1.3. This 1.3 is a matter of a convention. It doesn't come from any theory or any substantial statement from the statistical theory. So whenever we have overdispersion and we don't model it, what happens is that we underestimate the standard error, and we tend to have liberal p-values. That is, we tend to call as statistically significant things that are not. So the causes of so here in this table I outlined the separate possible causes of overdispersion. These causes are not mutually excluding. That is, you can have in a single data set several of them. So one is the inadequate modeling of the probability distribution, the GLM. That is, we could use, instead of the simpler Poisson distribution that has one parameter, the mean, we could use instead the negative binomial distribution or the quasi-Poisson distribution. So we might have an incomplete model in the sense that it has an incomplete set of explanatory variables. That is, if that is so and we have more explanatory variables, then add the variables and perhaps interactions when it's justifiable. Another reason might be that there are outliers in the data, outliers with respect to the model that is fitted. This could be identified using the Cook distances and the Pareto coefficients if you fit a Bayesian GLM. In this case, you could try to refit the model without the data and compare the parameter estimates between the two. There might be an excess of zeros. In this case, we may use an mixture model, and there are two brands of this: the zero inflated and the zero augmented GLM. This will be discussed in another video associated with this chapter. Another possible cause is that there is an excessive variation of the response variable. In some cases, it might be relevant to change the model structure by adding an observation level random effects. This would be explained in the videos associated with chapter 13. So in order to let's see how we can interpret the parameters of a count GLM. So let's assume that we have a numerical explanatory variable x, and that we are modeling the log of the mean of the response variable as a function of these numerical explanatory variables, and the goal of the game is, of course, to estimate the intercept and the slope of this parameter. So the relative change, we can also write the relative change of the mean for change of 1 unit in the explanatory variable as follows. So this is the change in the mean. The change in the mean this is the change when the explanatory variable increases from x to x plus 1 divided by the mean of x. This is what I mean by a relative change. So then we can, of course, as before, we can invert the link function after estimated parameters. This will allow us to this will give us the predicted mean of the response variable as a function of a set of values of the numerical explanatory variable x. So we replace this expression in the expression of the relative change, and we obtain the following. It's very simple, and then which can be simplified so as to provide that the relative change of the mean when the explanatory variable changes 1 unit is simply the exponential of the slope minus 1. This is relative or percentual change of that, of the mean when we change by 1 unit the numerical explanatory variable. This is, of course, valid for any GLM with a long link function, not just for the count GLMs. So let's go to our data analysis. So the goal of the analysis is to determine the effect of a set of biogeographical variables on the number of plant species in the Galapagos Islands. The Galapagos Islands are an archipelago with islands of many sizes, shapes, and ages. So I started by importing the data. There are data for 29 islands. The number of species range from 2 to 444, which is a very large number. And we can see also that the values of elevation, the elevation of the island, and the size of the island in square kilometers encompass 4 and 6 orders of magnitude. So it's very unlikely that the relationship between the log of the mean of the number of species is linear in these extraordinarily large ranges. One solution is to log transform these variables, which is what I am going to do. Here I log transform these two explanatory variables for no other reason that is unlikely that the relationship with the response variable is linear over such a large range. So I'm going to use QQ plots and cumulative distribution plots to compare the two distributions, the Poisson and the negative binomials, as the most adequate distribution to model the response variable. So I just fitted the use the package fit distribution, fit dist plus, whose main command fit dist fits the Poisson distribution to this response variable. That is, it estimates its parameters, and then it fits the negative binomial distribution to this response variable, which implies estimating the two parameters of the negative binomial distributions. With these fits, we can generate the following two plots. We see here the cumulative distribution function of the number of species. Here the goal of the game again is to see which of the two distributions, the negative binomial distribution or the Poisson distribution, is closer to the actual data. The actual data comes here in dots. Obviously, we see that the negative binomial distribution is a lot closer than the Poisson, and the same is shown in the QQ plots. Again, it's obvious that the negative binomial distribution is the best distribution to model this response variable. So the statistical model, therefore, is that the response variable has a negative binomial distribution with its two parameters, the mean and phi, the dispersion parameter, and we are going to make the log of the mean of the response variable a linear function of a linear combination of the explanatory variable with coefficients that we are going to estimate. So here we try to assess whether the response and the explanatory variables are related, and what we see is that we have distance to the nearest island, distance to Santa Cruz, which is the oldest island in the archipelago, the log area and the elevation here in the lowest row. We find that there doesn't seem to be a relationship between these two explanatory variables and the number of species, whereas there might be a relationship between the log area and the log of elevation with the number of species. The log of area and the log of elevation happen to be strongly correlated, and in this case we are going to select one of the two to be included in the model. I chose the log area for non-statistical reasons, and the non-statistical reasons is that I am a biologist and I happen to know that there is a topic in ecology called island biogeography, where the log of the area of an island is an important feature of the theory. So based on this non-statistical criterion, I am going to use the log area as the explanatory variable instead of the log elevation. So the frequentist model fitting, I started by standardizing the three variables that are going to be included in the model in order to be able to compare their coefficients. This was explained in previous videos, and I'm going to fit use the command glm.nb from the package mass. NB, of course, stands for negative binomial. These are the three numerical explanatory variables that are included in the model, and here the intercept simply is the value of the log of the mean number of species when the three explanatory variables are 0. The three explanatory variables being 0 means that they are in their mean values. So we see the intercept. This is the meaning of the intercept, the standard error with which this sampling intercept estimates the population intercept, and this p-value simply says that this intercept is significantly different from 0, which is of no interest in the context of our analysis. What we see here is that the slope of the log area is 1.3, meaning, and with a very small standard error, and this ratio between the two, between the estimate and its standard error, happens to be 10.7, which shows us that this partial slope is significantly different from 0. We also see here in the bottom that the ratio between the residual deviance and the residual numbers of degrees of freedom is very close to 1, which suggests that there is no over dispersion. So because these three explanatory variables are all in the same scale, they were standardized prior to the analysis, we see that a change in one standard deviation of the log area has a much larger impact on the number of species, on the log of the mean of the number of species, than a change in one standard deviation of any other variables. So again, I see no indication of overdispersion. So when the goal of the analysis is to evaluate the effect of these explanatory variables, this is the final answer, the model that we just fitted. When we are in an exploratory mode of analysis, we might wish to obtain a more parsimonious model. In this case, we might consider this as a starting point, the fitted model M1 as a starting point, in that it might be simplified. So taking M1 as a starting point, we generate other statistical models by deleting one explanatory variable at a time. This is accomplished by the command update that takes M1 as a starting point, and it deletes one explanatory variable at a time to generate the models M3, M4, and M5. So these descendant models are all, of course, special cases of M1, and they conform a nested set of models. We could use either the Wilks log likelihood ratio test or the AIC to obtain the most parsimonial models, that is, to select between M1, M3, M4, and M5. So here I am simply comparing M3, which is a special case of M1, with the likelihood ratio test, and this says that these models there is no statistically significant difference between these two models. So we could then choose between M3 and M1, and I would choose M3 because it's simpler. It doesn't have it doesn't have the distance to the nearest island. Likewise, when I compare the M4, which is a special case of M1, I see that there is no statistically significant difference, and I could then choose between the two. Between M4 and M1, I would choose the simplest, which is M4, that doesn't have the distance of Santa Cruz. These two analyses suggest that distance to the nearest island and distance to the Santa Cruz do not receive a strong empirical support from the data and could be perhaps eliminated. When I compare M5, the model that doesn't have the log area, I see with M1, a model that does have it, I see that there is a very high significant very highly statistically significant difference between the two models, and therefore log of the area is a variable that cannot be simplified because it generates a statistically significant difference between the likelihood of these two models, the parent model M1 and the descendant model M5 in this case. So when I use the AICs, I see that M1, M3, and M4 are all essentially have all nearly identical AICs, and there is a huge difference when with model M5. M5, I recall, is a model that doesn't have the log of the area. So based on these suggestions, this suggests to me that I could simplify the model and keeping only the log of the area as an explanatory variable, which again I provide here by fitting the model M6. Again, I see that the slope for the log of the area is significantly different from 0, and again then there is no overdispersion in this analysis, in this GLM fitted, suggesting that this GLM M6 models correctly the variation in the data. So in order to we assess the goodness of fit of the data by the residual analysis using the package Broom to gather the input. This is the fundamental input, and this fundamental input has this variable here is the deviance residuals, which are not recommended to assess the goodness of fit of a GLM. So instead we are going to replace this deviance residual with the Dunn-Smyth residuals. These are computed with the command simulate residuals of the package Dharma. This was explained in a previous video. So res.m6 holds the Dunn-Smyth residuals that are converted here in the next line with the command qnorm into a normal distribution, and I am writing these residuals in this data frame on the top of the std.recid variable. So I recall that this conversion does not force the Dunn-Smyth residuals to have a normal distribution. They would only do so would be so when the GLM fits adequately the data. So let's see the plots. The plots contain the residuals against the fitted values. We see a random scatter of point. If we divide this left half and the right half, we don't see a substantial difference in the variability of the residuals. Suggesting that the residuals have homogeneous variance. The QQ plots says that residuals are very close to the line of perfect fit, suggesting that the Dunn-Smyth residuals do indeed have a normal distribution. We don't see any pattern here when plotting the residuals against the explanatory variable log area. And in terms of the Cook distances, there are 2 points, but 2 points out of 29. It's very unlikely that this deleting these 2 points will change substantially the fitted parameters of this data set. So all in all, the model has a very good fit to the data. So the main results can be shown here in a table with parameter estimates and the 95% confidence intervals. The confidence interval says that the slope could be as low as 0.29 or as high as 0.44. This is a range of equally plausible values of the slope, relating the log area with the number of species that are compatible with the data and the fitted model. We can also obtain the conditional curves with the package ggfx. The main command is ggpredict, which gives us the log of the area, the predicted values, and the 95% confidence interval with which we obtain the following predicted curve. And we see that the conditional curve actually predicts pretty well the observed values, the observed number of species of our data set. So the Bayesian model fitting, we recall the statistical model, and we use the command getPrior of the package BRMS to obtain specifying family neg binomial to obtain the priors that need to be defined. I recall that the priors of the GLM are defined in the log scale, so we need the priors for the partial slopes of the 3 explanatory variables. We need a prior for the intercept, and we need a prior for the shape. The shape is the extra parameter of the negative element distribution that I forgot to put here in the starting point of the slide. So I'm going to define these priors more or less on feeling, on no journal. I provide some justification for this in the book. So the implications of these priors can be seen in the following plot. So I expect the log of the number of species to be between -5, which is a very small number of species, and +10 in the log scale, which is a very large number of species. I expect the partial slopes to be between -4 and +4, which is a very wide range, with a typical value or expected value of no relationship between the explanatory variables and the response variable. And as for the shape parameter of the Poisson of the negative binomial distribution, I expect this value to be very small. Very small means that it has a normal negative binomial distribution shape indeed. So I simply use the command BRM of the package BRMS, specify the Poisson, the negative binomial distribution that I want, the prior that I define, the warm-up, that is I'm going to discard 1000 iterations. I want 3 chains, and I'm going to parallelize the calculations. I'm going to request 2000 iterations of the Markov chains. So the summary of the model contains the marginal posterior distributions of the model parameters in log, not log, it's scale, in log scale, and the metrics are the r hat values and the effective sample sizes, showing that the convergence of the algorithm. We have this for all parameters of the fitted model. These are the means of the posterior distribution. These are the standard deviation, which here correspond to the standard error of these marginal posterior distributions, and the 95% confidence intervals. This shows that the 95% confidence interval of the slope, partial slope of the area, there is a probability that this partial slope is between there's a 95% probability that this partial slope is between 1.02 and 1.6. We see that the r hat value suggesting that the three chains have converged to a common stationary marginal posterior distribution for each parameter, and we have plenty of statistically independent estimates in our chains. Because these explanatory variables were standardized prior to analysis, we can compare the mean of the posterior distributions of their slope, and again show that a change in one standard deviation of the log area has a much larger effect on the mean of the number of species than changes in the other explanatory variables. So we can visually assess the convergence of the marginal posterior distribution for each of the three chains graphically. This can easily be seen in the graph in the left, and the autocorrelation shows us that all in all, except perhaps for one of the chains, for one of the parameters, we have essentially nearly many statistically independent estimates, which is two good signs of a well-fitted Bayesian GLM. So we are going to proceed with the model selection for the Bayesian GLM. We are going to use the Lu criterion that is equivalent to the Watanabe-Akaike information criterion. This was explained in chapter 7 and in video 11 of this series. So the first thing is that we generate a set of models. That is a model starting with the model M1. We generate a model M2 and delete one of the explanatory variables, and then we add the Lu criterion to this to the resulting model. The resulting model is called M2.brms, and we do likewise for the models in which we delete the distance to Santa Cruz and the log area. Now we have therefore four models, M1, M2, M3, and M4, each of which has the Lu criterion. We are going to compare the Lu values, and we actually see that the M2 is a model with the lowest expected log posterior distribution, but essentially that the models M2, M3, and M4, M1, M2, and M3 essentially are identical, since the difference in this criterion, in this Lu criterion, are all within the standard error, but the M4 model has a very large difference. So this again shows that models M1, M2, and M3 are essentially identical. This means that deleting these explanatory variables, distance to Santa Cruz and distance to the nearest islands, don't make much of a difference, whereas the M4 model without the log area is substantially worse than all other models, suggesting that this is an important explanatory variable. We again arrive to the same result in this model selection exercise to which we arrived for the frequentist version of this model. So in order to assess the goodness of fit of the data, we obtain the Dunn-Smyth residuals with the using the package Dharma, for which we need to first obtain the posterior predicted distribution. Here are the posterior predicted distributions, and with these posterior predicted distributions we use it with this command create Dharma to obtain the Dunn-Smyth residuals. that are then converted to a normal distribution only if the model fits well using the usual command. We then create a data frame with all the input necessary for the plot of the residual analysis, and this input is these residuals we just obtained, the explanatory variables, the predicted values, which are here obtained, which are here shown, and the Pareto K coefficient that tells us whether each data point has an important effect on the fitted parameters of the Bayesian GLM. We, by the way, obtain the percentage of the variation explained by the model, and the model M1 explains 74.7% of the variation of the response variable. There's an explanation of how to obtain the index of overdispersion for this Bayesian GLM, count GLM, so please see details in books if you want to obtain it. So the plots again show us that the residuals disregard the right hand side of the plot A because there are only 2 points. So we essentially see that by and large, there's a random scatter of points in this plane. We see the same thing in plot B, D, and E, which are the plots showing the relationship between the Dunn-Smyth residuals, the converted Dunn-Smyth residuals, and each of the explanatory variables. We see that the Dunn-Smyth residuals are all seem to have a normal distribution as a sign of a good fitting model, and that all points but 2, all data points but 2, are in the very good range for the Pareto K coefficients. Only 2 of the values are in the good range. So all in all, this Bayesian GLM has a very good fit to the data. We can also obtain the PV checks from the posterior predictive distribution. I recall that the posterior predictive distribution is a set of predicted values of the response variable that are predicted by the fitted model, as it was explained in chapter 7 and in previous videos of this series. So we have 29 data points, or posterior predictive distributions are values of the we ask for 1000 iterations, so we have 1000 rows. Each of these rows is a set of values of the response variable for each of the 29 points, for each of the 29 data points of our data set. With this posterior predictive distribution, we see that the model is able to predict this. In thick blue line is the observed density curve, and in pale blue lines are the set of 1000 density curves from the posterior predictive distribution. We see that the model is able to predict as a typical realization, meaning that it's more or less in the middle of this jungle of predicted curves. We observe the predicted the model predicts the observed values as a typical realization. We also see that here are for each of the 29 data points, we see that with the exception of a few cases, here are the mean and the 95% credible intervals in pale blue lines, that most of the observed values are within the 95% credible interval. So the model seems to have a very good predictive ability for these two features that we asked for. Finally, we can obtain the conditional curves simply by replacing here in the blanks between the dots the name of the response variable for which we want to obtain the predictions, and this sets all other variables to 0, that is to their means, because we standardize the explanatory variables prior to the analysis. And from this we obtain the following predictions, which is the relationship between the response variable and each of the explanatory variables. There is a pretty weak relationship for the distance to the nearest island and the distance to Santa Cruz, and a very strong relationship between the number of plant species and the log of the area. Here we have the mean of the posterior distribution for each of the parameters and the 95% credible interval for each of the parameters. So in this video I explained the GLMs with a count variable, starting with the explanatory data analysis to be followed by the frequentist fitting and the Bayesian fitting. I hope that you found this video interesting and that you take a look at the next video in which I explain how to model counts whenever there is an excess of zeros in this response variable, as it is often the case with counts. Thank you very much.